So here is a presentation about paired t-tests, and on top of this presentation I really want everyone to go ahead and look at the calculator corner that's in the textbook. It'll show you how to do a two-sample t-test on your calculator. Now I'm going to walk you through a problem that is in your textbook, so if you'd like, you are more than welcome to follow along. It's on page 755. And it's about whether or not smells can actually help us learn. So the test included of 21 subjects who worked on a paper pencil maze while wearing a mask. Now there were two types of masks. There was an unscented mask and a floral mask. And what we were measuring was we were actually measuring their average time on the maze. So they did 3 times with the floral mask, 3 times with the unscented mask, and they averaged each of the times. Now it's important to note with this study, randomization is important because the subjects tend to improve their times as they work on the maze repeatedly. So when I do a maze for the very first time, it's typically going to take me a little longer versus if I do it for the third time. So here's our data, and to analyze this data, what we're going to do is we're going to actually do what we did with the confidence intervals, the two-sample t-test for intervals, or the paired t-interval, where we had 2 lists of data and we actually found the difference between the lists. We combined them into a list. So what we're going to do is we're going to put our unscented data in list 1, and then we're going to go ahead and put our scented data in list 2. Alright, now if you're following along, go ahead and put that information in your 2 lists. And what we're going to do is we're actually going to subtract the scented time from the unscented time. So I'm going to do list 1 minus list 2, and I'm going to actually store that in list 3. So just like the intervals, we've taken 2 different data sets, 2 paired data sets, and we're combining them into one by finding the difference between them. So the question we're investigating is, do we have evidence that the scented masks significantly improve performance? So we actually need to look at what does it mean for them to improve performance? What would it look like in list 3? So we did unscented minus scented times. Now, if unscented time really was longer, if we did worse without the floral mask, we got a longer time. If I had a longer time minus a shorter time, I'm expecting to see positive differences here. A positive difference would mean that the scented mask did in fact help performance. So I'm going to conduct my hypotheses. So I'm checking whether or not the average time has improved. So I'm going to start by assuming there's no improvement. So you'll notice right here, I'm starting by assuming that the mean difference is 0. There was no improvement. And my alternative is going to be that there was some improvement, a positive change. Now remember, I'm measuring the mean difference in times to complete the maze for all people in the population from which the subjects were drawn. This problem isn't very specific of the people in the study, so I can't clarify my population much more. Now, I also note at this point that I'm going to use a 5% significance test. Now, to check my conditions, I need to check SRS, normality, and independence. I'm also going to identify that I'm doing a paired t-test for means now. Now, the data comes from a randomized matched pairs experiment. The randomization is good. However, I can't necessarily say it's an SRS. So you'll notice here I identify proceed with caution. Now, normality, I only have 21 subjects, so notice I cannot apply the central limit theorem. However, if I show a stem and leaf plot or a box and whisker plot, you'll see that the distribution looks fairly normal. Now, I would be doing this of my list 3 data, so that data that you stored in list 3. So I have no reason to doubt normality, so I'm going to assume. And with independence, I'm willing to assume independence because it makes sense that there's at least 210 people that could potentially take this maze, but the key here is that, of course, an individual subject's average time with scented and unscented are not independent, so that is important to notice. Whenever you do something with and without a treatment, the same individual, independence is something that you need to note. Finally, I get to my calculations, and I'm going to apply 1-bar stats of list 3 in order to get my sampled statistics. So I get my average difference of 0.9567 seconds, standard deviation of 12.5479, and my degrees of freedom is n minus 1, which in this case is 20. Now from this I get my test statistic, my t, remember this is a t, because I don't know sigma. Alright, so I take my sample minus my hypothesized mean difference of 0, divided by, now remember, this is my standard error in the denominator because I'm applying S rather than sigma, standard error down here. And I get a test statistic of 0.349. Now if I go look on the table, if I go along my row 20, my degrees of freedom of 20, and I look for this test statistic of 0.349, notice that as I go, my values are getting bigger. So 0.349 actually falls just to the left of this very first value. So if I actually go and look up at my p-value, that tells me that my p-value in this case has got to be even bigger than 0.25. Notice to the right of this value it gets smaller, which means to the left it must be getting larger. So I know my p-value has to be greater than 0.25. So therefore my p-value is greater than 0.25, and it actually, if you run the two sample t-test on your calculator, like the calculator corner walks you through, you will get the actual p-value of 0.3659. I can't get the exact p-value on my table because I only have these possible values listed, but on the calculator you can get the actual p-value of 0.3652. Alright, now that takes me to my conclusion. Now, I do not have enough evidence to reject my null hypothesis because my p-value is greater than my significance level of 5%. Therefore, the data does not support the claim that fluorescence scents improve performance. In fact, the average improvement was so small, we saw it was only 0.96 seconds compared with the 50 seconds that the average subject took when wearing the unscented mask. So I can see numerically that it didn't seem to make a really big difference. Alright, now one thing that I want to remind you of with T procedures is something called robustness. Now remember, if a procedure is robust, it means that even if a condition is not met, the calculations still end up being fairly accurate. Now a little reminder here, in 10.2 we talked about this, and we said a procedure is robust in the following situations. If I have a really small sample size, like less than 15, your distribution needs to look pretty darn normal. We really don't want to have any outliers or major skewness. If I have a medium-sized sample, like say 15 to 30, it's okay unless there's anything major, any major outliers or major skewness. And lastly, once we get a sample size greater than 30, we're okay even if our sample appears skewed, my sampling distribution should be approximately normal according to the central limit theorem. Alright, remember, as n increases, the central limit theorem ensures the distribution of our sampling means becomes more normal and the t distribution becomes more accurate for calculating p-values. Alright, now last but not least, I just want to touch real fast on power. The power of a statistical test measures its ability to detect deviations from the null hypothesis. Now in practice, we often carry out the test in hope of showing the null hypothesis to be false. So higher power is important. High power means that this test is going to have the ability to detect deviations from our hypothesized mean. Remember, power of the one sample t-test against a specific alternative of the population is the probability that the test will correctly reject the null hypothesis. And that should be on your note sheets from chapter 11. Alright, here's a little problem you are more than welcome to try if you'd like to pause the video and check your understanding of the different types of errors that we talked about last chapter, in chapter 11. Go ahead, pause this, and try this out. Let me know if you'd like the solutions to it, and I'd be happy to provide them so that you can check your answers. Alright, so that's my video on paired t-tests and their similarity to paired t-intervals. I hope that helped, and let me know if you have any questions.